Hi, everyone. Thanks for coming again. We're going to go through and do what's called Ken Shoulders number four. I'm just keeping it simple so that we keep them all in order and whatnot. And again, this is some information that Chris Beskar, who is Ken Shoulders' business partner, gave to me to sort of let everyone go through it. And one other thing I was going to say was I did talk to Chris Beskar a few days ago, and we talked about setting up another interview for just after when Trump comes back. So we'll have some more information and possibly a couple more interviews after that point. So today's just going to be a short little session here where Brendan will read through some of this work and we'll from Ken Shoulders. So I'll let you take it from there, Brendan. Thank you.
Okay, thank you very much, Eddie. Okay, so today's lecture or talk is going to be EVO propulsion basis by Ken Shoulders.
Now, this one is really, really important because it shows EVOs coming in and striking an aluminum foil, and then they're looking at what happens underneath, essentially. So Brendan will kind of go through and sort of point out where those arrows are pointed and what's going on, essentially.
Okay, so this slide shows edge view of coated aluminium foil being struck by EVOs. And in the diagram at the top left, we have I think it's incoming EVO strikes. I can't read that very well. It's not clear enough.
Yeah, yeah,
But EVO
incoming EVO strikes. Yep,
and this one
and
here,
and then the one beside it on the right says reverse propelled material.
edge view of
And
aluminium foil down here, and
yep,
then reversed EVO region forward
yep,
propelled over here.
yeah. So you can see with the forward propelled section how it almost looks like they're little rockets or little, little bursts of energy. And that's basically showing that the EVOs can be used for propulsion because that's basically what they're trying to describe here. And so they come in, they strike the foil, and then the forward ones cause this propulsive effect to occur where there looks like there's energy
Forward there.
flowing out the bottom, right? And then the reverse EVO regions are slightly different. And I don't know if Ryan, do you want to jump in here and maybe talk about what the difference between the forward and reverse EVO regions are?
Is Ryan there? Ryan,
Yeah.
he may have gone to the
Yeah.
toilet.
Okay. Okay. Well, let's move on to the next one then. So you can see in this one, it's a little bit different setup, but they've got these incoming EVOs, and then they've got these very thin streaks coming out. So what we're seeing a variety of different effects occurring here, and I think as we move in here, they might talk a little bit about what's going on here with these effects.
So this states
So
edge view of coated aluminium foil being struck by EVOs. At the top, it has incoming EVOs. At the bottom, thin streaks.
yeah. So again, it's showing that there's different effects occurring here. So let's go to the next one, and it'll show some more of the what happens. This is the reverse side of the foil. So you can see that some of them made it through and some of them didn't. So the ones that didn't make it through, created these craters, and there's in the top left hand corner there is a crater that or well, it's a reverse crater that has a hole in it. So basically, it created
this one
that
here,
crater.
this one, this one here,
Um,
this one here.
yeah, exactly. That one there. That one shows a, a reverse crater like a dome, and then a hole in the end of it. So obviously, the energy did escape that one, but there are a few of them here that you can see that the energy didn't escape. So it's just showing all the different effects.
So
The
it
back,
states SEM of aluminium foil reverse side.
yeah,
CEM meaning SEM,
SEM.
sorry.
So scanning electron microscope. Yeah, that's what they would have used to see that. And if we go to the next one, it'll show a little bit more about what we were talking about. And I'll just let you read it if you can see it, and if not, I can, because I've got the hard copies in my hands here.
Okay, I'll just read this. So it's the scale is 100 micrometers. Um, this part here states large explosive eruption um uh due to
Do
high momentum transfer between EVO and coating material. And on the
yeah,
right-hand side, it shows normal 20 micrometer EVO passage through coating and aluminium foil. Note offset angle.
yeah. So again, these are the ones that created, that dome or that reverse crater on the other side, and the energy was able to escape. And like they're saying, there's something going on with that offset dome. And this is all research that even we can dive into at some point. It's just stuff that was done with Ken Shoulders research. And the next one is just sort of the setup that they used to for one of the experiments here, which is kind of cool.
Cross-section drawing of photographic exposure of EVO boring operation. So at the top over here says silicon
Carbide
carbide epoxy um, mix.
mix. Yep,
Then we got EVO boreholes,
yep.
aluminium foil, 200 mesh copper grid, forward propelled material, aluminium base plate, photographic film.
Yeah, so this is an experiment, and obviously it's got to do with the forward propelled material. Remember at the beginning there, we're trying to describe and figure out what that was all about. So this is one of their setups, or one of Ken's setups, I would assume, or someone that's doing this research that talks about how they did it, basically. And I'm not sure that this setup was where the photographs at the beginning came from. I'm not quite sure about that, but as maybe we'll move on here and we can probably see if explains that a little bit.
Um, photographic film exposure of EVO penetrations. Splatter on the top left, and then no splatter on the bottom right.
So so this is the outcome of that experiment, obviously, that we just saw. And he's seeing splatter and no splatter. And I'm not 100% sure, this is just my intuition saying this, that because we have black EVOs and white EVOs, it could be possible that the splatter section is from a black EVO, but it also just could be that the EVO had very, very high velocities and was causing the splatter from that as well too. That part we don't know. Again, if someone wants to dive into some of these experiments and recreate them, there could be a lot of knowledge gained from that. Um, on the next one, oh, there should be one before that.
One before this? One
Yeah,
before this?
yeah.
That one? That's the splatter.
Um,
Is this the right one? Was it? Is this the right
I
one?
think you, I think you might not have it then. It says point projection image of UVO reversal in space, and then 200 mesh screen image from varying distances. And it
Would you
just
want to send?
shows,
Do you want to send it to me quickly, or what do you want to do?
no, let's not worry about it. Let's just go into the reading here. It'll be too disruptive if I try to do that right now.
Okay, I'll
We
just read
should
at the
have we
top.
should have probably went through them all and made sure we had them before we started, but that's okay. Yeah,
Sequence
sorry, go ahead, Brendan.
sequence of EVO propulsion events. Forward motion. An EVO is launched from the electrode of a pulsed high voltage source. The EVO travels through atmospheric pressure air, strikes the surface of a curved mixture of
Cured
silicon
mixture.
carbide and epoxy cement spread on an aluminium foil. The EVO bores through the mixture layer as well as the aluminium foil, producing a clean 20 micrometer diameter borehole on the way in. Some holes are bored just short of the aluminium foil, and others bore completely through with excessive energy, largely due to the variation in silicon carbide layer thickness. Excessive
Interesting.
energy holes expel fluidized silicon carbide at a high rate, at a high velocity in a forward direction.
Yeah, interesting. So now we understand a little bit more about the forward motion part of it that they were talking about in the experiments. And the next one, we're going to talk
Next
about
slide.
the reverse one. Yeah.
Um, Burst motion. For a large percentage of holes, EVO bores completely through the silicon carbide and aluminium foil and then reverses its direction, likely due to an open circuit, electrical impedance mismatch.
That's
It,
really interesting. Wow.
this reverse motion of the EVO carries with it all material it has disrupted to atomic form and propels it towards the top side of the silicon carbide mix.
Hmm.
The material is ejected with high velocity in a reverse direction to the entry direction of the EVO. A strong emission of light from a point source is recorded on the film, confirming the fact that penetration of the aluminium foil and charge acceleration has occurred. Not a trace of ejected material is found below the hole on the photographic film recording. So sorry, I'll write that again. Not a trace of ejected material is found below the hole on the photographic film recording the operation, indicating no rocket-like action had occurred.
Wow. Some pretty interesting things here. Again, stuff to unpack for anybody that wants to try and do the experiment. Again, essentially, right? Which is probably something that we are going to want to do eventually once we have the facility to do that. So yeah, we can go on to the next one. It's just the conclusion.
Conclusion: a a heretofore undocumented form of very powerful and efficient propulsion is displayed, indicating a connection has been made to something outside our usual sensory system.
That's a pretty powerful statement, saying that there's a powerful and effective propulsion system here. And this is the basis of all of the charge cluster.
Efficient propulsion, powerful and efficient propulsion, and effective as well. But
Yeah, so this is the essentially what Stevati Aerospace is using and will use in their designs for their anti-gravity craft, including the hover car from Chris Beskar. The next couple ones, Brendan, are not from this presentation, but something that Ryan and I had discovered the other day when we were talking about this transmutation that occurred. And this is a slide from that first one, is a slide that we actually did a presentation on already when an EVO was shot through a copper slug and they found transmutation that occurred on the other side of it. So what was really interesting was a conversation I had with Ryan the other day when he was telling me that he had, I think, 26 pages of this book from the Proton 21 laboratory
Yeah.
that was in St. Petersburg. So yeah, do you want to talk about this? Because this was fantastic. Sure. That we found this, right?
Yeah, so while I was at Carmen's house, Bob mentioned the research from the Russian Proton 21 lab, and he showed me his copy of a book. It is available online, but it's pretty expensive. But it's called Controlled Nucleosynthesis, and that one of the pages he showed me was the page that showed this same micrograph. So this came from the Proton 21 lab.
Yep. Yeah, and that's what we had discovered. So I think if you go to the next one, Brendan, you might actually see what Ryan sent me. And then we're going back and forth going, holy cow, this is actually the same thing, right? And then there's I think I took a screenshot of us conversing about it as well. But so this is the actual thing that Ryan sent me that came from the Proton 21 laboratory. It's exactly the same picture.
Yeah, so just briefly, it was a Soviet research lab, and what they found was that with high voltage impulse discharges, they were able to get these transmutation events that had a wide variety of elements, like almost all of them.
Yep.
They show a chart, and I sent those pages to Ed. So that's a really interesting confirmation of Ken Shoulder's work, because they basically did all of that and then some.
Yeah.
And so the implication here is that at least for particle accelerator physics, the implication is that this could be used in a similar way that, for example, the 88-inch cyclotron at Berkeley Lab is being used for right now to synthesize super heavies. And I think it would there may be a possibility there that this means of doing it could lead to a more controlled means of doing so. Therefore, higher yields of specific products, target products, and possibly even if you have a target material that has a high neutron count per nucleon, stable super heavies, anybody?
Yeah, exactly, right.
Exactly. And I should just briefly mention my friend. I won't mention his name here, but he works there on the 88-inch cyclotron. And when I shared those screenshots of those pages with him, and he looked through them, he actually went and bought a copy of that book himself.
Which I'm going to do as well. Yeah, for
Right
sure.
on.
Didn't you tell me also that that Proton 21 laboratory got moved from Russia?
Yeah. So one of the other things that Bob mentioned was that um, the the experimental apparatus, the material, I'm not sure exactly what, but the um, some of the stuff or all of the stuff, I don't know which, from the Proton 21 lab eventually ended up uh, in Batavia, Illinois at Fermilab
Okay.
and at Brookhaven. And Fermilab and Brookhaven are two of the big accelerator centers as far as development of new accelerator tech.
Yeah.
Uh, so I found that particularly interesting because, how long ago
Yeah.
was that and where is it?
Yeah, exactly. And I think what you were describing a little bit there, Ryan, was the next generation of particle accelerator technology.
Yeah,
Is what you're
that's
kind of, and we've had some discussions about that, right?
yeah, and this strongly confirms my initial suspicions after reading the letter from Feynman to Ken Shoulders.
Yeah, exactly. Because you told me that there was something in that letter, even that Chip actually pointed out that was very important to some of the discussions that we had the other day. Yeah. Hopefully at some point, if everything goes or comes to fruition with what we were talking about, we might be able to recreate this exact experiment, actually, perhaps
That'd be great.
in a lab, right? That's the ultimate goal would to be to try and confirm some of this stuff. And I think the last one, Brandon, might be just me taking a screenshot of me and Ryan in the signal chat, realizing that we had just we had just figured out this is all from the Proton 21 laboratory.
So,
And
so I'll just read the
oh yeah,
self-organizing nucleosynthesis in superdense plasma. Figure 2.4, crater-like destruction of an initially uniform target anode that serves as an energy concentrator. From the surface cathode side under the impact of the process initiated by electron beam.
yeah, very cool.
Sorry,
And
Ryan, could you mention the name of the book again, mate?
Controlled nucleosynthesis.
Thank you very much.
and this
Welcome.
is just Ryan's or my signal, I think, with Ryan and the guy going back and forth and realizing that we were looking at the same picture and that all the same information, and again I want to thank you, Chris Beskar, because this is who gave me this, right? So we have to
SEM stands for
scanning electron
Scanning.
Standing
micron.
Yeah.
Electron Microscope. Okay.
Yeah, yeah, yeah. So this is essentially research that was done by the Russians that was shared with Ken Shoulders because they're basically trying to recreate his experiments, and then the lab is moved to America, which is very, very interesting. And then Chris
And then poof.
Beskar, not long ago, sends us this information, which is pretty interesting in itself too, right? So it's cool. So yeah, it's just the SEM is the same, and Ryan's said, "Yep, it sure is the same." So that's pretty interesting, actually. So does anybody have any questions or anything you guys want to add? Chip or Ryan or anyone?
That's it. Yeah, that's it. So we can come back to here.
Before we stop the recording?
Do you want to start the recording now?
Yeah, if no one's got any other anything
Okay.
else
Thank
to
you
add.
everyone for listening.
Yeah, thank you again, and we'll be back again once more with work of Ken Shoulders. Thanks to Chris Beskar. We always have to thank him for sure.
Okay.
Yeah.
Cheers. Bye then. Bye.